Okay, so we went over what this application binary interface is. Now we're going to go a little bit further into our discussing the computer overall. Now, when we talked about the API, we talked about being able to communicate between different programs, both inside and out of your computer. And the ABI, which is your binary interface, is the interface between binary program modules. But the computer overall has a bunch of parts that need to operate together effectively, right? So we all know some of those parts. Let's take a look at and consider some of them, right? When we think about our parts, we think about the computer parts, we think about the input and output devices, right? Your keyboard, your mouse, your monitor, hard drives, all those things that allow you to get information into the computer and also to retrieve that data. There's also the battery, your memory, your CPUs and GPUs. Now, CPUs and GPUs have gained a lot of popularity within the past, decade or so because of their capacity to handle a lot of data at once and really for people to be able to run neural networks and different types of machine learning on those particular devices, right? The more GPUs you have, generally, the more powerful your computer is and the more processes you can run. But these also make an impact on how we code and how we develop our programs. So as we think about that, let's consider our input and output devices, right? You have your keyboard and your mouse. You know you're going to use that to send some sort of command and do something to get a specific response from your hard drive, right? If I type in my keyboard device, google.com, I want it to actually go to that specific site and pull the information down. Your hard drive is also part of your input output device, as well as your monitors, and even some of the things we see in terms of the networking capabilities. But in addition to our hardware devices, we also want to consider how these things operate together, right? If I'm looking at for example, if I go back a couple slides and I'm talking about my memory, right? My RAM, your RAM memory, and also your read-only memory, all of that is going to impact how much you can do, how fast you can run these operations, and whether or not the computer is going to be overwhelmed. Now, remember, previously I talked about kind of these three stages of what you want to consider for computer architecture in your programming design and developing your particular code, right? And those three major areas are your power, your processing, and your memory. Now, your power includes things dealing with your battery and your power supply, anything that's going to provide juice to your computer. Your processing, as we talked about a little bit, includes your CPU, your GPU, and your memory, and then the memory itself. Now, the reason that memory is kind of listed twice or is listed as a subset under processing is because, as we stated before, and most of us may probably know, the more memory you have, particularly your RAM or your random access memory, the greater capability you have to do multi-level processing or to do different things all at the same time, right? So that's going to impact not just your how much you can store, but also how much you can do, how many functions, how many programs you can run all at once. And then, as I stated before, your random access memory and read-only memory are also important. Now, the reason that the memory component is important because every time, right, we talked about this, every time you get data, every time you send a command or you receive a command, that's written to a specific register in memory, right? So the more memory I have and the more control over that, the more I can do with whatever code and program that I write. So as we're thinking about all these things, right, let's remember this, PPM, right? PPM is going to be power processing and memory. How can we go into or think about programming in a way that optimizes these three components, right? You want to first not only understand it, but one way to develop these programs a little bit more effectively is to think of them sort of in an abstract mode or in an abstract way. So we have these things called models. Now, the von Neumann architecture actually allows you to model your particular device, right? It allows you to model how you're going to handle your programming language, right? The von Neumann model is a computer architecture model that really shows and demonstrates the data flow for programming or for coding. So let's go ahead and get into that and how we're thinking about that, right? Your von Neumann model is really a reference for your computer architecture and data flow. Um, for this particular model, the programs and the instructions are all stored in the same memory. That means you have one memory bus and you are, sending your programs and your instructions both in that same memory bus. Now there's another model called a Harvard architecture, which has two separate buses. But for this particular model, it's just one memory bus for both of them. And the reason that that's important is because as you think of this conceptually, when you're doing programs, when you're sending out these instructions, because they're in the same memory, you want to think of, okay, what do I want to send to this address? And what do I want to maybe wait on, or how do I sort of stagger these commands to optimize my ability in terms of programming these particular commands? Now, the other thing is that for this particular model and this architecture, it actually treats instructions as data, right? So it's looking at everything as a data flow. That's how it's representing what we're doing in terms of programming. And you can really think of it kind of like a stored program on a computer. If we consider the hardware kind of an infinite loop that we have access to and the ability to write to, this is a good model to look at in terms of just exclusively thinking about how to optimize your programming and your coding. So let's go ahead and take a look at how this is structured. So something to consider is for a von Neumann model, and this will be an exam question. So the von Neumann model is going to always have four components. Some of them may be represented a little bit differently, but you're always going to have memory. You will have some sort of control unit, typically a CPU, a processing unit, or a arithmetic logic unit, and you're going to have your input output devices. Now, your input output devices, sometimes they're combined into one, and that's fine. But these are going to be your four cornerstones or your four main meats, your main things for this model, right? And you'll see here the way that it models the information or the way it displays it is your memory is the main the main attraction, right? How am I going to get this information in and out of memory, right? Your control unit is writing to the memory and is receiving, information from the memory. Your processing unit is writing to the memory and is receiving information from it, right? In addition to that, you have the way that the control unit itself is communicating with the processing unit. So this is all represented in this kind of diagram, right? If I say, hey, I want to run this for loop, right? And what I want to do is every 5 seconds, I want to send out a beep from my computer to let them know, hey, 5 seconds has passed, and I want to do this. Let's say I want to do this 12 times to represent 1 full minute. Well, I say, okay, this is my control unit. Where can I store? Where's the sound stored in memory? And how do I get it out? And then how do I remember what the counter is set at, right? That's going to be someplace in memory. Okay, I decided, all right, I did the first count. Okay, send the information. Now I'm getting that back. Now I also have to send the information to the processing unit to process all that data and be able to get this sound and send it out to whatever your speaker or your hardware component. And then, of course, you're receiving all this information because if we start from the bottom up, the first thing you want to do is the user is going to give you a command for what they want to do, and then it has to be processed and sent through to the CPU. So that's your von Neumann model. Now, what you guys are going to do for your first recitation is you're going to give your own explanation of it, but it should all have these key features, right? So I'm repeating this so that we can, really understand it. One, it is a computer architecture model that represents programming or coding as a data flow process, right? It treats programs and instructions as data. When you look at these arrows, they're representing the data that's flowing in terms of your program. Another thing you want to remember is that it's always going to have these four components, right? Some representations of the von Neumann model do include additional things as well, but your four cornerstones that you're going to have are going to be your memory, your control unit or your CPU, your processing unit or your arithmetic logic unit, and your input and output devices. Those are going to be the cornerstones of what you're going to do, right? Where the first thing you're doing is your program, you're inputting information, right? We're starting from the bottom up. You're going to input information that's going to go to your processing unit. It's going to be communicated to the control unit, and then that's going to go up to your memory. And then also, it's going to have an interface with the processing unit will have an interface with the memory itself, right? So just keep that in mind for your four components that you will have for your von Neumann model, right? So now that we understand a little bit about the von Neumann model, how can we use this and what's the next step? Well, when you think about and you understand how this works, you're able to implement effective programming, right? If I know, okay, if I'm considering just one memory bus for my coding, that means I need to think about which part of my code are going to require a lot of memory, and how I can kind of stagger that, not to overwhelm it or run into places where where there might be contradictions or where they kind of bump into each other. So, and again, these are things you will remember for the key features of the von Neumann model are going to be right here on this slide 20, one memory bus, program model, and it also contains these four items: memory, a ALU processing unit. You know what I'm missing from here? It should be memory, a control unit. I'll make sure I update those on the slides. But this is actually going to be it's going to be memory, your control units, right? Your processing unit, and then also your input and output devices. All right. So as we think about all of these things, right, we're thinking about ways where we can kind of understand our computer architecture a little bit better. We want to consider not only how we can understand it better in different language types, but also how can we use all of this to become better coders, right? So some languages are going to they're going to provide faster interactions and responses than others, right? So let's get into it. Your first one that we're going to look at is the machine language. Now, your machine language is binary code that is used to talk directly to the central processing unit, right? As I stated before, the CPU only understands things in ones and zeros. So your machine code is going to be in ones and zeros in this machine language or binary code. The benefit of this language is that it is closest to the hardware. It's going to be the fastest to operate. And from machine code, you can write instructions to the CPU directly. In addition to this, it also has the shortest execution time because you don't need to interpret it, because you don't need to convert it. If you wrote something in zeros and ones directly, it's going to be able to execute a lot faster than some of the upper level languages. Your second level language, or the next level up, is called your assembly language, right? We don't read in ones and zeros because it's just daunting. It's a lot of information. So there is something called assembly language, which was developed, which is more of a human readable machine code. So some of it might be hexadecimal with some minor commands that allow you really to read the information a little bit more clearly than you would in binary code. Now, this does need to be converted to binary code, which means that it's going to have a longer execution time than machine language will. But it also has a shorter execution time than our upper level languages, which we typically use like C, C++, Python, etc. So now stage 3, right? We go from machine language, excuse me, to assembly language. And then the next level up are these high level languages. They are human readable. They do need interpreters or compilers. And what that means is there is a difference between an interpreter and a compiler, right? And that's going to be important because the languages with interpreters are going to be a little bit slower. They're going to be slower in terms of developing your executable code. So an interpreter, what it does is it goes line by line and converts the code, which means it's going to take longer, where your compiler will take the entire file or the entire object and convert it all at once, right? So the interpreter might be beneficial because it allows you to see, okay, what's my problem with this particular line of code, but it's going to take a lot longer than a compiler. Some people use C because it doesn't necessarily need an interpreter, but you can use more of a compiler with it. Now, the high-level languages are absolutely more versatile in functions. You have a greater capability of telling the hardware what you want to do than you would in sort of this assembly language code, which might be limited in terms of its functions. But as I stated before, these high-level languages are going to have your longest execution time. And as you notice, as we're traveling up, you're getting further and further away from the actual CPU. So let's kind of look at some of these examples, all right? Machine language is pretty simple. It's going to be zeros and ones. So there we go. There's an example of that. When we look at assembly languages were those languages that were used in the 19th century, in the 20th century. Like and some of them are actually still being used today, by the way. Some of the programs at my job are actually in I think they're in Cobalt, not COBOL. But COBOL, BASIC, Fortran, these are these assembly language that were pretty popular and were used back in the day to write these programs. And then we have the higher level languages that we use today, like C, Python, Java, React, LabVIEW, C++, it goes on and on in terms of what we use for those high level languages, right? And keep in mind that the further you go up, right, the more you go this way, the further you are from your actual hardware, from your actual CPU. All right, so now that we understand our programming languages, and when you know that the further you are in your higher level language, the longer it's going to take you to execute things, right? You also want to consider what you want to use when you're writing this, right? As I was stating before, C is a language that we selected and we chose because it takes a little bit less time to compile than, say, Python. Where Python, a lot of your programs are actually based in C and C++ anyway, so it's like converted and then it's compiled for some instances. So it just takes a little bit longer for it to execute its functions, and it's wasteful in memory in terms of that, or wasteful in processing in terms of that. So let's talk a little bit about the operating system, right? So when you think about parts of a computer, right, you're going to need something that is going to mitigate and manage all the things that you have, right? What tells the API what can be used first and second or last, and what tells the programs which thing to run? It's going to be your operating system. The operating system is like the head chef of our restaurant. It tells which applications get the software and what things can be done simultaneously, right? Because some things can be run side by side. You don't need to run everything sequentially, or you don't need to run everything one after another. Some can be run simultaneously. This the operating system also gives permission, or asks the act for permission from the operating system to run these particular components within our software. And we know our common operating system, there's this big debate. There's Windows and Mac or Apple operating systems, and there's Linux as well. And all of these have the same function in terms of being that supervisor or that head chef that dictates how things will be run within our restaurant, right? Now, when we want to consider, as we're thinking about this, as we're thinking about the OS, right? This OS, or this operating system, is going to tell you how to run all this stuff, right? And it's also going to take into account or be impacted by these three factors, right? Um, how long, what's my power like, what's my processing like, and what's my memory like, right? A lot of operating systems will say, hey, this is taking up a lot of power or a lot of memory, so we're going to stop that function so that we can operate, right? Or it's going to let you know, hey, this particular application is taking up a lot of power, or your power is low. So what do we do about that? When we think about these factors, we want to think about how long can my program run, right? How long can I continue to do this particular process? And how much power does this process require? Is it going to be constantly pulling from my battery? Is it going to be constantly pulling from my power supply? Or is it just using a little bit of power? The other thing we want to think about as we're coding, and the other thing the operating system is thinking about, is how quickly can it access and run these particular applications, right? So when we're programming, we're thinking about, hey, how fast can this run, and how many tasks can it run simultaneously? And finally, last but not least, how much space do I have left in memory? And how often do I need to access this memory in order to run these particular processes, right? Because the operating system has an overall view of kind of all of this, a lot of the information. It's something else that's going to consider as well. But we want to think about, how long do I need, how much memory or space do I need to perform this action, right? If I create a program with a lot of variables, right? For example, if I'm writing something in Python, and I choose to make this variable an array as opposed to a dictionary, right? That's going to have a different, or a different impact, right? Do I want to make this an array, or do I want to make it a dictionary, right? What's going to have more space or less space? Because if I'm taking up all of this memory with one particular way to do that, then that means I'm going to have less space for running my processes, right? You remember, your instructions and your data in our von Neumann model or one data flow, right? So if I'm using all of this space on variables, or all of this space on data, that means when I try to send an instruction, I'm going to have less room or less space to send the instruction that I want to send. So as we think about that, right, power is going to be the first thing that we look at. How can I optimize my power? And what impacts my power? Well, let's look at Moore's Law. Moore's Law says that the number of transistors or components are going to double each year, right? For some of the Intel chips that we have today, they have over 1 billion transistors, right? And as we continue to increase these, as we continue to go up in the number of transistors, excuse me, we'll also see that we need to reduce the power consumption, right? We can't have the same power consumption for 100 transistors as we do for 200, right? We can't use those same methods, because you're going to start getting a lot warmer in your CPU. So you have to find a way to reduce this power, excuse me. The more transistors you have, the more transistors you have, the more power you're going to consume. Now, eventually, you get to a point where you can't really minimize your power. Eventually, you increase to a point where um, the number of transistors you're going to add are going to exceed whatever power limit you desire. So what do we do? Well, one of the ways we can mitigate this is by limiting the number of transistors that are used, right? If I have, 100,000 transistors, right, I don't need to turn them all on at the same time. I don't need to use all of them for the same process, right? It's staggering. It's using, different cores, it's using these at specified times, right? If I can stagger the power of it, that means rather than turning 100 transistors on and consuming 50% of my power, maybe I only need to turn on 10 and consume 10% of that power, right? Or 5%, right? In addition to that, what we can do is write parallel programs to coordinate between these transistors and the way that these are used. Also, and from a hardware perspective, of course, you can implement better cooling solutions, which you notice that your computer has these fans. I remember as part of working on laptops, one of the problems that HP computers would always have is their graphics would die because their cooling wasn't sufficient enough to reduce the heat, so it would get overheated, and the graphics in there and the card, everything that was associated with it would just basically die out. So we want to implement good cooling solutions and also write the effective programs to coordinate between these transistors. All right, so that was number one. That was your power. All right, power, PPM, power processing and memory. All right, now that we talked about power, we're not ready to talk about memory. Now we want to discuss how can we mitigate or maximize our processing? How can we mitigate issues we might have, things that would slow our processing down? How fast can I run my process, and how many tasks can I run? So how do we do? What do we do about that? And how can I speed up my particular processes? Well, one of the things that can help us with that is identifying the particular components we have, right? One thing you want to think about is your clock speed, right? The faster your clock speed is, the more you're going to be able to do in it, or the faster you're going to be able to do these things in a particular time frame. So how can we speed up the performance of our clocks or these particular devices? Well, one of the things we can use to kind of represent that is something called Amdal's law. And what that shows is really showing the relationship to how improving a particular part can speed up. How much of that does that actually speed up my processes overall, right? If I could improve one transistor, is that really going to speed up my process as opposed to improving something else? Well, the way that you would determine that is by looking at this particular equation, right? So what you'll see here is we have the total speed up time, right? It's going to tell us how much we're going to actually increase or how much we're going to speed up in time. And P represents our percentage, right? What percentage of the time is this part used? And then the speed up of that part. Now, what's interesting to note or important to note here is that your speed up performance is proportional to the percentage of time that the device is in use, right? So if you only have a device that's only used 1% of the time, even if you increase that by 100%, you're not going to be as effective, as opposed to if you have a device that is used 50% of the time, increasing that by just a little bit will have a greater impact on improving your or speeding up your processing time overall. Right. So this is the equation for that particular law, and things to consider when you're trying to speed up your performance. All right, so we went through power, right? Your power and the ways to mitigate that, or things to consider there, are Moore's law, right? The more transistors and things that you have, the more you're going to consume power. We talked about ways to improve that. We went through your processing, right? Which is Amdahl's law. We can basically determine how fast or how much improving a particular component will actually improve my speed of time. Now we're going to go into option three, which is our memory, right? How do we improve our memory? How do we improve how we use our memory? How much space is available and how often does it need access, right? This is a question that I asked before, and this is particularly for your particular program. How often is this register accessed? Now, there is this occurrence called the memory wall. And that's where you get to a point where you have increased your memory, but you didn't see an increase in the performance of your device, right? So what happens if, okay, I started out with 4 gigs of RAM and then I put in 64 gigs of RAM, right? I'm going to see some sort of increase there. I'm going to see an increase in performance, but there will come a time when you don't see as much of a performance increase as you desire, right? So one way to mitigate that is to have a cache that delays the operations between memory and processing. So now if I'm trying to process a lot of commands, I can kind of delay it and use my cache as a buffer to allow me to maximize my memory. It's similar to the issue that we have in terms of consider like a highway or rush hour traffic, right? If you have this all of this memory and there can be times where, maybe from at like I don't know, 11, not many people are using the road, right? But then you hit 5 p.m., everything is using the road, and you have all these cars that are trying to get through this one thing, and you have jams, right? Same thing can happen in memory. There can be a time where you're not accessing that, right? Where you don't have a lot of the programs or the functions running, so it doesn't need to access those registers in memory. But when you have a lot of programs and you're at certain times trying to access all of these registers at once, you're not going to get the real performance that you desire. So you can use the cache to say, okay, what I'll do is I'll stagger some of these moments. I'll stagger some of the traffic so that the roads themselves can be clearer and I can really maximize the amount of space that I have in memory. So let's kind of look at and summarize what we have already discussed, right? Why do we want to understand hardware? Why do we care as programmers? It just seems like why is it important? Because the more we understand hardware, the more effective we can be in programming, right? So since I know that my memory is going to impact my ability in my code, I want to write things, one, that's not going to over exaggerate or exhaust my memory. If I can find ways to store things with less space, right? If I can create a data structure that has less space to store the same amount of information, I'm going to use that because I won't waste that register. And then I can use that memory register for more of my commands, right? Since we're thinking about memory and your data being in that same data flow in terms of programming. All right, so now we can make our programming more effective and more efficient. In addition to that, understanding the hardware will allow us to mitigate our memory power limitations, your memory walls, and other things that may come up that may basically cause issues with your code, right? It can inhibit your ability for your code to run. What you also want to consider is that today's computer systems have a lot going on. They're extremely complex with a lot of information, right? So you want to be able to understand it so that you can just write a better code. As we look at processors, right, we talked about Amdal's law, right? The faster your processor is, the more you're able to do in a certain amount of time. It also allows applications and multiple applications and domains to be run, and a faster processor will allow you to have more speed in whatever applications or tasks you want to run. So that's pretty much the summary for this particular lecture. You want to consider all these things and really look at those components that we talked about, right? Understand what the von Neumann architecture is. Understand how to run this information, and really understand what it means. Not just so you can explain it for the recitation, but also so that you can just have a basic understanding of how to code better in your programming. So that is it for this lecture. Thank you guys so much for joining me. And hope that you enjoy the rest of your particular day.